EPO AI patents. Write technical effects statements that convince. Welcome. If you're filing AI inventions at the EPO, the key is showing a technical effect, not just clever math or business value. Your effect must be credible, verifiable, and repeatable. Anchor every AI feature to a concrete technical problem, like memory bottlenecks or sensor noise, not vague promises. Avoid abstract benefits such as better insights or smarter decisions. Instead, explain how your method changes what the computer or device actually does. By the end, you'll know how to frame AI claims so examiners see a real improvement in hardware, systems, or data handling. The EPO looks for clear improvements in how machines operate. Examples include improved computer performance, lower latency, less memory usage, or reduced energy per operation. Better resource management or data transfer also counts, like smarter caching, reduced bus contention, or compressed interconnect traffic. Effects in the physical world matter. Enhanced sensor or actuator control that stabilizes a drone or reduces motor jitter is technical. Even specific data structures are eligible when their form enables a technical function, such as cache-friendly layouts or index schemes that speed SIMD operations and reduce cache misses. Certain contributions don't carry technical weight. Business, administrative, or mental activities are out, even if powered by machine learning. Purely aesthetic or presentation-only changes, like prettier dashboards, don't help unless they alter system behavior. Dataset content or labels as such aren't technical. Describing better annotations isn't enough without a system-level effect. Likewise, model accuracy on non-technical tasks alone, e.g., predicting churn, is not technical unless it triggers a measurable improvement in computing performance or control of real-world processes. Pitch your invention with a tight chain. First, state the technical problem in operational terms. For example, high DRAM traffic causing latency spikes. Next, describe the AI feature that addresses it. Sparsity, quantization, a scheduler, or a cache-aware layout. Then explain the causal chain to the hardware or system. How weights skip compute, how tiles fit SRAM, how threads avoid stalls. Finally, name measurable indicators and conditions. Latency at sequence length 4K, joules per inference on GPU-X, or packet loss under 10 gigabits per second load. Make the logic testable. Quantify the effect with system metrics. Latency, throughput, cache misses, joules per operation, DRAM bytes moved, or GPU occupancy. Provide baselines and controlled comparisons, same model, same data, changed feature. Reference reproducible tests or prototypes, scripts, hardware specs, dataset splits, and seeds. Ensure claims align with embodiments in the description, so examiners see how the feature maps to the improvement. If you assert a 20% speedup, show the setup, variance, and why the mechanism generalizes beyond a one-off benchmark. Plausibility beats promises. Include implementation details, not only theory, memory layouts, kernel steps, and buffer sizes. Disclose architectures, parameters, and constraints, such as tile dimensions, sparsity thresholds, or scheduler policies. Address limitations and expected ranges, where the effect holds and where it degrades. Write with definitive language based on what you built or simulated. Avoid speculative words like could or might. The goal is to let a skilled person reproduce the technical effect from your description at the filing date. Target effects that move hardware needles. In training, claim faster convergence via memory locality, e.g., sharding gradients to keep hot tensors in SRAM. For inference, show reduced compute via sparsity or pruning, skipping multiplications and cutting power. For data, adopt a format enabling SIMD or cache-friendly access, such as tiled key/value blocks. In systems, use a scheduler that reduces GPU stalls or I/O waits by overlapping kernel launches and prefetch. Each angle ties an AI feature to a measurable system improvement. Use this template. By feature, the system reduces/increases. Metric under conditions, because technical mechanism. Example, by tiling attention keys/values in SRAM, LLM inference cuts DRAM traffic 35% at sequence length 4K, reducing latency 18% due to fewer cache line evictions. Notice the clear feature, metrics, test conditions, and mechanism. You can swap in training or systems claims, e.g., by block sparse gradients, training reduces joules/step 22% on A100 at batch equals 512 because skipped max lower SM utilization without underfilling warps. Keep it specific and testable.